So what was the last topic we saw? We saw resistors in series, right? Okay. So what have they started in school? So yeah, we'll get started with the next topic. Okay. So that is going to be resistors in parallel, right? So there's something which you already know, but yeah, we'll be discussing about this. Okay. So when we take the resistors like this, I call this as R1, R2, and R3. And let's say they are connected across a potential source of V. Okay. So first thing that we can make a note here is when we say resistors are connected in parallel, the thing is potential drop across all resistors is same. So that is one point. And secondly, current supplied by the battery will get split across each resistor such that sum of individual currents across each resistor will be equal to the total current supplied, right? So these two are the known facts, right? What are we saying? One is potential drop across all resistors is going to be the same. And secondly, current supplied by the battery will get split across each resistor such that the sum of the individual currents across each resistor will be equal to the total current that is supplied by the battery itself, right? So first make a note of this. Finished? Shall I proceed? So listen, if you look at this battery, right, it has a positive terminal and a negative terminal, right? So when you take this positive terminal, let's say the potential of this terminal is V. Listen to this carefully. The battery has a potential difference of V. So potential difference between whom? Potential difference between the positive and the negative terminal. The question is, if this terminal supply, if the positive terminal has a potential V at this point, then what I can do is I can take the potential of this point to be 0, so that the potential difference between the positive and the negative terminal is going to give you the potential drop across the battery. Okay. Now let me explain what is the meaning of this first statement. Potential drop across each resistor is same means the potential difference across each resistor is going to be the same. So the point that I'm going to tell you now is also used to solve problems. So concentrate and listen to this. Whenever there are 2 points connected without any passive element between them. When I say passive element, they can be either resistor, capacitor, or something called as inductor. So when 2 points are connected with the help of a wire and there is no passive element between them, then those 2 points are said to be at the same potential. Meaning of it, if this point is at potential V, then this point is also at potential V. Why is it so? Because these two are just connected with the help of a wire and the resistance of a wire is considered to be 0. Okay. So what will be the potential of this point? And potential of this point is also a V. Similarly, what is going to be the potential on the other side? When the potential here is 0, they both are connected with the help of a wire. So here also it is going to be 0. Here it will be 0 and here also it is 0. So if you look at the potential difference across each resistor, how much is it coming to? The same V. Is that point clear? Okay. Now the second thing is, if I say that the current supplied by the battery is I, right? Current supplied by the battery is I, then this I will get split across each resistor. Let us say it is getting split as I1 here, I2 and I3. Okay. Then the sum of the individual currents, that is I1 plus I2 plus I3, will be equal to the total current that is supplied by the battery. Right. So if you observe, it is exactly the reverse scenario that happened in the case of a series connection. So in series, what happened? Current was same, but the potential was getting added. Here it is exactly the reverse. Okay. Having said this, if I write the mathematical equation as I is equal to I1 plus I2 plus I3, my job is to find what is the value of I1 in terms of potential difference and the resistance. Similarly, I2 and I3. Okay. So if I observe, I know the potential drop across R3. How much is the potential drop across R3? It is V minus 0, which is V only. So can I apply Ohm's law here? So if I apply Ohm's law, what will I write? V is equal to I3 into R3. Here, V is equal to I2 into R2, and here V is equal to I1 into R1. So applying Ohm's law across each resistor, applying Ohm's law across each resistor, what will I get? We'll get V is equal to I1 R1. So from this, can I write I1 is equal to V divided by R1? Similarly, V will be equal to I2 R2, which implies I2 will be equal to V divided by R2. And V will be equal to I3 R3, which implies I3 is equal to V divided by R3. Right? So if you observe these values, you can take them and substitute it in this equation. So right hand side is sorted. What is the right hand side? It is V divided by R1 plus V divided by R2 plus V divided by R3. Am I right? So I'll take these three values, substitute it here. This is what we are going to get on the right hand side. But what about the left hand side? So first thing we need to understand that how is the equivalent circuit for this going to look like? So how is the equivalent circuit look like? You will have a resistor RP, which is going to replace R1, R2, R3 such that you have the same job done by RP individual instead of these three, right? So if I take the potential here to be V, the current supplied by this battery is still going to be I only, right? So here if I apply Ohm's law, what do I get? I'll get I is equal to V divided by RP. So I'll take this V divided by RP and substitute it in the left hand side. So it will be V divided by RP. So what is that going to get cancelled? V is gone, which implies 1 divided by RP will be equal to 1 by R1 plus 1 by R2 plus 1 divided by R3. Right? So this is going to be the expression for what is the relation? Relation between the equivalent resistance and the individual resistances. Okay, so make a note of this. Battery. Huh? ஏதாவது ஒரு பேட்டரி உள்ள இருந்து ஏதாவது இல்ல இது இல்லப்பா உள்ள இருக்கும்ல Done? Shall we proceed? Okay. So we have seen the concepts related to few derivations, right? Like drift velocity and how to derive the relation between drift velocity and electric current. From there, we saw how to derive Ohm's law, right? Then applications of Ohm's law, what we saw is how to derive the expression for resistors in series and parallel, right? Now we are supposed to go to the next important topic. So write down the heading as so the next topic that we are going to discuss is EMF of a cell, okay, which is called as electromotive force. It's called electromotive force. Okay. So let me explain this with an example. See, observe. I have a battery. Though I'm talking about a cell, let's understand with the help of a battery. I have 3 different batteries in my hand, right? So you're able to see this one. This you would have seen it most of the times. And this also, right? So if you see these 3 batteries, for example, if you go to a shop, right, this is very commonly used. You call it as a AA battery. If it is thinner than this, you will call it as a AAA battery, right? So for this, you have a positive terminal and a negative terminal, right? The question is, what is happening due to this positive and the negative terminal that this is able to supply energy to us? The question is, when we talk about potential difference, what is potential difference? It is the amount of work that needs to be done to bring a charge from one point to another. So whenever we talk about work, we need to apply some force, right? So since I told force, electromotive force does not literally mean force. I'll tell you what it is. Okay. So somebody or some particle should be moved inside due to the application of some force, right? Now, what is going to happen is, if you observe, the manufacturer has given me a data here. For example, if I get this battery, then I can understand that it is written as 9 volt. Means the potential difference that will get generated when you connect it across the circuit is 9 volt. If I buy this, generally, though you call it as AA battery, if you look at the value that is written here, it is 1.5. Right, this is 1.5 volt, where in general remotes, for example, if you look at this AC remote also, there are 2 batteries that are used. If you look at them, they appear to be in parallel, but they're actually in series. We'll discuss about what is the meaning of cells in series. Okay, meaning positive terminal is connected to the negative of another. I'll explain it later. Now our concentration is understanding what is EMF. Right. So are you able to get the perspective? Here it is 9 volt. Here it is 1.5 volt. On this also it is written as 1.5 volt. Though the size is different, let us not worry about why this is happening. Our objective is understanding what exactly is EMF. Right. So this is what the manufacturer has given us. Right. Meaning, when you buy this, you believe that it is exactly going to give you 9 volt. But you know, in reality, you will not get that 9 volt. You will actually get a value less than that. Okay. That is, when you connect it across any circuit, you will definitely get a value less than that. Okay. So here you need to understand one thing. We had been discussing about potential difference, right? So EMF, though the name is misguiding us, saying that it is some force, it is not force, it is also potential difference. So EMF is basically the potential difference of a cell in open condition, meaning in this condition, it is not connected across any circuit, right? So in this scenario, this 9 volt is actually not the exact potential difference, you say this is the EMF. You say this is actually EMF. Are you able to understand? So EMF basically means the potential difference across a cell in which condition? Open condition. So I hope I'm clear. So you understood what is the meaning of open condition, right? You just buy that and come, you don't connect it across any circuit, right? When that happens, then that potential difference is what is called as EMF or electromotive force. But I told you one thing, when you connect this across a circuit and try to measure the potential difference across this, let's say you're using a voltmeter to measure it, you will not get the value as 9 volt. You might get somewhere around 8.8, 8.9, depending on the battery's age. If it is a new one, it will be closer to 9. If it is already used, maybe it will be lesser than. Okay. So it is going to lose its energy with time, or else this would have had infinite life. No, you buy one battery for lifetime, we could have used it. Right? That doesn't happen. So it is going to die at some point. Right. So the question is, why is that happening? Why is there a potential drop that is taking place? Why is EMF and potential difference that is going to be in the closed circuit not exactly the same? For that, we need to look at what is happening inside a cell. So basically, when you consider a cell, right, it consists of a liquid inside it. So what is the name of that liquid? It is an electrolyte. So what does this electrolyte do? Whenever you supply energy to it, it can get split into ions, right? So inside this electrolyte, what will happen is you will have two electrodes placed like this, which is called as anode and a cathode. So positive is anode and the negative is going to be cathode. When this is there, let us assume that this electrolyte is NaCl. So what will happen to it? It will get split as Na plus and Cl minus. So we'll use the basics of electrostatics to understand what will happen. If this is the positive terminal, which ion will have the tendency to go and get attracted? So Cl minus will travel in this direction and Na plus will travel in the opposite direction. It is going to go in this direction. Am I right? Now the question is, these ions which are moving, they are actually passing through a medium, right? So when they're passing through a medium, logically what should happen? They will be experiencing some resistance. You're able to understand what is happening? There will be some resistance that is going to exist, and that resistance which is offered by the electrolyte to the flow of the ions is called as internal resistance, because it is happening internally. So it is called as internal resistance, and internal resistance is represented by the symbol small r. So try to understand the concept here. When I discussed about parallel, right, I drew the resistors and I wrote the resistance values in capital R. Generally, we use capital R for external resistors and small r for internal resistance, just to differentiate and make people understand that you're talking about external or internal. Okay. So till now, when I derived, right, see, for example, if you take this expression also, I wrote the potential drop here as V. Actually, what is this V? This is EMF. Okay, because what I did is I considered ideal situation. In the sense, I didn't take any internal resistance associated with the cell. Are you able to understand? So here what is going to happen in real-time situation is there will be some resistance offered by the electrolyte to the flow of charges itself, and that resistance is what we call it as internal resistance, due to which what will happen is when you connect a cell across a circuit, let's say its potential drop is V, this V will actually be equal to E minus I into R, where this E is called as the EMF and small r is called as the internal resistance. So if you observe, this is what happens. That is the reason why EMF and potential drop will not be the same. So this EMF is going to be the potential difference that is occurring under open condition. So from here, it is going to lose some energy so that this is going to be the net effect. Okay, why this expression has come, I'll explain it slowly. I'll show you the derivation of it. Okay, but as of now, try to understand that this is what is going to happen. Okay, so till now, what I did is, when I take the value of small r to be 0, so small r to be 0 is considered to be ideal situation, meaning I'm talking about a cell which does not have internal resistance, which is not going to happen at all. If I substitute R is equal to 0 here, then what will happen? V will be equal to E. Okay, this is one way of understanding. Means the potential, there might be a question, when can the potential drop and the EMF be the same? When is it possible? When you consider an ideal situation where the internal resistance of the cell is 0. That is one thing. And the second case is, let's say internal resistance is existing. Okay, so this is case 1. So the second case is, let's say R is not equal to 0, but if I say I is equal to 0, what is the meaning of I is equal to 0? It is open condition. When can current not flow through a circuit? Only when it is open, right? So this is the meaning of open condition. When I put I is equal to 0 here, what will I get? Which implies V will be equal to E, and this is the definition I gave you. Are you able to understand? So this is the definition. So EMF is equal to the potential difference across a cell in open condition. Are you able to understand this? Okay. So please make a note of this. So the next topic that we are going to discuss is, see, till now we understood that whenever you need to solve a circuit, most of the cases we would have used Ohm's law, right? But is there a law where you can use it when things get complicated? That is, you can use Ohm's law in one situation. What is it? Ohm's law is applicable when you're able to simplify the circuit and able to bring it to one resistor and one potential source. If it is like this, if I say here the potential drop is V and here the resistance is R, then I can write the value of I as V by R. Whereas, had the same circuit been with two resistors and one potential source like this, right? If I say the current is I, then I cannot write it as V is equal to I into R1 and V is equal to I into R2. Can I? I cannot do that. I'll be able to write the potential drop only across individual resistors. Meaning, if I say that the potential drop here has been V1 and here it has been V2, then I can write V1 is equal to I1R1 and V2 is equal to, V1 is equal to IR1 and V2 is equal to IR2. Am I clear with this? Right. So here it is simple. What you can do is actually they are in series. You will make it as a single resistor by finding the equivalent value and then do it. But there will be certain scenarios where you will have more than one battery and a complicated circuit, which we generally call it as a network. During that scenario, right, it is not easy for us to solve that problem using only ohms. Because what is that we are supposed to do? You need to make those two batteries into one. Sometimes it will be possible, sometimes it will not be possible. When you have those kind of circuits, then you need some other law which is going to help us solve them, for which we have two important laws called as Kirchhoff's current law, or we call it as Kirchhoff's junction rule. Okay, this is one of the laws. Okay, and the second is going to be called as Kirchhoff's voltage law. So this can be called as KCL in short form, and this can be called as KVL in short form. Okay, so we will be using these two laws. So they are not like individual laws. They both should be applied simultaneously in the same problem. Okay, so if you have to come to this, you first need to apply this. That is how they are related, about which we will see individually. Right? Shall we get started? So first I'll explain, then you can write. First, we'll talk about it's called as Kirchhoff's current law, which is also called as KCL. See, suppose I have a circuit like this. Right? Where the potential drop is V. Now let me say that the current supplied by the battery is I. This is the total current it is able to supply. So this I is going to travel from higher to lower potential in this loop. Right? So there is a loop. The circuit is closed. It's not open. So when it is going here, you are able to see a junction here. So this point is either called as a junction or you call it as a node also. It is also called as a node, NODE. Okay. So at this junction, what will happen is this current I will get split. So that's obvious, right? So the current will get split in such a way. If I take the current which is flowing here as I1, and let me call this as R1 and R2, for instance. If I call the current here as I1, and if I call the current here as I2, then this Kirchhoff's current law states that at a junction, right, at this junction, the amount of current entering the junction is equal to the amount of current that is leaving the junction. To be more specific, the algebraic sum of the currents at a junction is always a zero. I'll explain that. Okay. So what did we say? The first way of stating it is sum of currents entering a junction is equal to the sum of currents leaving the junction. I hope it is obvious and it is clear, right? So meaning of it is, if I take this point to be P, look at the currents that is entering the junction, means which current is traveling towards P. It is I. So sum of the currents entering the junction is equal to sum of the currents that are leaving the junction. Which two currents are traveling away from it? Obviously, I1 and I2. And this is going to be the mathematical expression for Kirchhoff's current law in this problem statement. Are you able to understand? Right. So this is one way. Or what I can do to this expression is, can I write it as I minus of I1 plus I2 is equal to 0? Can I write it in this way? So you look at this, I minus of I1 plus I2 is 0. So here, the alternate way is algebraic sum of the currents at a given junction is always a 0. So what is the meaning of this? Why did I say algebraic sum? Because if I take the current entering the junction to be positive, then the current leaving the junction I consider it to be negative. So I minus I1 minus I2. So that is the reason why I use the word algebraic, because I cannot use the word vector, because current is a scalar quantity, right? So that is why algebraic sum of the currents at a junction is always a 0. So these are the two ways to state Kirchhoff's current law, and this is how the mathematical expression is formed. So you can change it according to the problem. Okay. The last point related to this is, you got this equation, okay. If you observe, it is looking like something is conserved, meaning something is supplying and something is taking. So can I say that the amount of current supplied is equal to the sum of the currents that are extracted? Right. So when that is the case, then the Kirchhoff's current law can be said that it is based on the concept of conservation of charge. So KCL is based on the phenomenon of conservation of charge. So this is also one question that can be asked. Are you able to understand? Right? So make a note of this. Let it be. That's not a problem. That's not taken. That is why I told it is based on conservation of charge. If that is the case, then it should have happened in the case of Ohm's law also. So after the resistor has experienced the after it has opposed the value only, that value of I1 is going to come into picture. This will practically work also. It's not a theoretically stated one. If you take an ammeter and try to measure it, your theoretical value and the practical value should match. Okay, that value of I1 and I2 that is coming is it's taken into consideration after the resistor has done its job. Okay. I1, I2, and I3 the potential drop across, right? Potential drop across this and only then you will get P and the R. the value of the resistance will also control how much current is up. That is where the resistance will come in. Do not change the value of I1 to something. Initially, that is decided. I can actually do this and show to understand. All you need is a multimeter. Measure and see. Maybe a slide between these. Take an ammeter. Not sure if you know what is the ideal. What is the resistance of an ideal ammeter? What is the resistance of an ideal ammeter? 0, right? But it will not be 0. There will be some resistance exist. Similarly, what is the resistance of an ideal voltmeter? It should be infinity, right? Meaning it should act like an open circuit. When resistance is infinite, current through it will be 0. That is how it should work, but it will not happen. If you see the actual practical voltmeter's resistance, it will be somewhere around 5,000 to 6,000 ohm. Means it will still take in some current. That is the reason why the potential difference and EMF are not the same. You're able to understand. So when you do this practically also, you will get nearby values, which can be considered to be accurate. That is what I'm trying to say. So to put it simple, for the question that you asked, these are all pre-decided. So resistor has nothing to do here. Everything is decided. It has supplied the total current. The circuit, it knows that the circuit has these 3 resistors. Based on that, it will control the value of that. Okay, imagine it like that. So to put it simple, this statement is what is Kirchhoff's current. Is that clear? Okay. So the next one is Kirchhoff's voltage law, which we will also call it as KVL. So next topic that we'll be discussing is Kirchhoff's voltage law, which is called as KVL. So obviously, in the previous scenario, when we spoke about current, here what should be spoken about? You need to speak about the potential drop, right? That is the voltage, right? The question is, when you have to speak about KCL, all that you need is a junction. Listen to this carefully. All you need is a junction. You're not concerned about whether the circuit is open or closed. Okay. Whereas when you need to speak about Kirchhoff's voltage law, all you need is a loop. When I say loop, you need a closed circuit. So I'm taking the simplest circuit that is possible. Okay. One minute. So basically what I did is, I took a circuit which contains an external resistor R and there is a cell with some internal resistance smaller. So cell means a positive and a negative terminal, right? Along with some internal resistance. When you put it within a box, it is understood that it is a cell with some internal resistance. Okay. So if I solve this problem using Ohm's law, if I want to calculate what is the current that is flowing through the circuit, let's say the cell is supplying current I. Then can I write I is equal to potential drop? What is the potential drop across the circuit? It is E divided by, listen to this, E divided by, what I'll do is I'll treat this internal resistor as external resistor. If that is the case, can I say capital R and small r are connected in series? Right. So it will become E divided by capital R plus small r. This is going to be the amount of current that will flow through this circuit. What I did is I applied Ohm's law. Right. So I took that only for you to relate it to Kirchhoff's voltage law. If the problem is this simple, you can go with Ohm's law itself. Don't get confused that you need to use Kirchhoff's law here, not necessary. Okay. So I'm going to state the law here. So it states like this. It is the algebraic sum of potential drops across each element in the circuit is a 0. Algebraic sum of potential drop across each element in the circuit is a 0. So here also, if you observe, I use the word algebraic sum because we need to understand one thing, that where is energy being lost and where is energy being gained. Okay. So to understand that, listen to this. For you to apply this law, what did I say? Algebraic sum of potential drop across each element in the circuit is a 0. Right. If you look at this circuit, how many elements are there? When I say elements, they can either be elements which supply energy to the system or they can be elements which take energy from the system. If you observe, there are both kinds. You have resistors and you have a cell. So resistors draw energy, cells give energy. So totally how many elements are there in this? 3. Capital R, small r and E. So to all those values, I need to find what is the potential drop across each element and need to assign a sign because I'm using the word algebraic. Okay. So how to assign the sign is, it is very simple. There is a rule that we are going to follow. Okay. If at all we are moving, so I'm not talking about current, don't get confused. So here, if you observe, the current is going in the clockwise direction, right? If I take this to be the loop ABCD, see, then the name of the loop will be ABCDA. You should always start and end at the same point. So when you have this kind of a loop, observe the direction of current. So you know that the current is going to flow in this clockwise direction, right? And we also know the fact that current will flow from higher to lower potential. So mark this point as H and this point as L. Am I right? Because if this is the direction of current, A is at higher potential, B is at lower potential. You come here, there is no element, leave it. When you go from C to D, current is flowing in this direction. So which one is higher? Right is higher or left is higher? Look at the direction of current. So right is higher. So with respect to you, right, no. So right is higher. It flows from higher to lower potential. Are you able to understand? Whereas for a battery, there is nothing decided by the current. The battery itself has a higher and a lower potential. Am I clear with this? So here, understand, if at all you are going from higher to lower potential, you tend to lose energy. It is very simple. If I take an object, right? If I take an object and just drop it, it is traveling from higher potential energy to lower potential energy. It is losing its energy. So after you write this H and L, let's say you are moving across the loop in this way such that you go from A to B. When you go from A to B, you are moving from higher to lower potential, meaning the potential drop across the resistor is considered to be negative. When you move from higher to lower, you consider it to be negative. But what is the potential drop across this resistor? You know the current across this? How much is the current? I multiplied with R. So I into R with a negative sign. Right? When you go from C to D, what is happening here? You're moving from higher to lower. So what is happening across this resistor? There also you're losing energy. Across this resistor, energy is lost. Of how much energy are you losing? Minus I into small r. Whereas across the cell, you're moving from lower to higher. So whenever you move from lower to higher, you gain energy. It is going to be positive, right? So plus E. When you talk about the battery, you will write it. You write only the potential drop across it or the EMF across it. Whereas for resistor alone, you need to multiply the resistance value with current so that becomes the potential difference. So the algebraic sum of the potential drop across every element put together is a 0. So if I rearrange this equation, what will I get? I'll get E is equal to I into capital R plus R, which implies I will be equal to E divided by capital R plus R, which exactly matches with this value. You're able to understand? So both mean the same. Okay. So one last point I would like to mention here is KVL is based on the concept of conservation of energy. So it is based on the concept of conservation of energy. Okay. So that is why I used negative and positive sign for losing or gaining energy. Okay. So just do me a favor. No, can you take a screenshot of this? I have to give the laptop inside. Can someone take a screenshot? Or I'll do it. Wait. You understood the concept, no? See, I've shared the screenshot in the group. I've shared it already. It's fine. I've shared it. You can make a note. So that last point alone, you can make a note. It is based on the principle of conservation of energy. So I'm removing the HDMI cable. It will get cut. Okay. Sorry, I have to remove this.